This is our pre-lab video for our heat of vaporization of water lab. And sometimes we abbreviate that like this. In this lab, we're also going to find the heat of fusion, which is the delta H of fusion. Just a reminder of what those numbers actually mean. The delta H of vaporization is the amount of energy needed to boil water. And then the delta H of fusion is the amount of energy needed to melt solid ice. We should talk about the theory behind these parts, part 1 and part 2, so that we know what kind of data we should take. In part 1, when we're trying to find the delta H of vaporization, if that's the amount of energy that's required to boil a substance, really that means it's the amount of energy that it takes to make a liquid into a gas. And to do that, you need to break the intermolecular forces. So we say that the delta H of vaporization is the amount of energy required to boil, but that also means it's the amount of energy required to break the intermolecular forces of that substance. Now, if the delta H of vaporization is low, it's really easy to break those intermolecular forces, and it's easy to make this substance into a gas. If we've produced a lot of gas molecules, the pressure of the gas is going to be high because we have a lot of gas particles in the gas phase. We actually call that the vapor pressure. And another way of thinking about vapor pressure is the partial pressure of your substance. So when the delta H of vaporization is low, we're going to produce a lot of gas, and the partial pressure of that gas is going to be high. When the delta H of vaporization is high, it takes a lot of energy to break the intermolecular forces, and it's hard to make that substance into a gas. And because not many molecules are going into the gas phase, the vapor pressure here is going to be low. So we can see that there's a relationship between the delta H of vaporization and pressures. And there's also a relationship with temperature, because as the temperature of a substance increases, evaporation increases, and the partial pressure would increase. The relationship between pressure, temperature, and delta H of vaporization can be seen in this equation that we call the Clausius-Clapeyron equation. And there's actually two forms of this equation, so I'm going to talk about both of them really quick. If you measure just two pressures and two temperatures, we have one form of the equation that looks like this. So this is the 2-point form because you're just measuring two pressures and two temperatures. But if you measure two pressures, so those are two partial pressures and their temperatures, R is the gas law constant, you can find the delta H of vaporization. But if you're able to measure more than just 2 points, there's a version of the equation that looks like this. The natural log of the vapor pressure, so those are the same partial pressures as we would have had before, is equal to negative delta H over vaporization, like this. Okay, so this is a multi-point form, but what's kind of good and bad about it is that you need to be able to make a graph. So that's good when you only want to measure 2 points, but usually when you have more data, your errors average out and you get better information. And so there's actually another version of the equation that allows you to take many data points and put them together to find the delta H of vaporization. And it looks like this, that the natural log of the vapor pressure, so that's the same pressure as what we had before, is equal to negative delta H of vaporization divided by RT plus a constant. Now this is the one that we're going to use in this lab because we're going to be able to take multiple points of data. And kind of the pros and cons of this, pros, you have a lot of data points, so you tend to get better numbers for the delta H of vaporization using this equation than you would using this equation. So those are the pros. The con is that you have to take many data points and you have to be able to make a graph and use that graph to find the delta H of vaporization. So in part one, we're going to be looking at the delta H of vaporization of water by studying the partial pressures of water. We're going to use this form of the Clausius-Clapeyron equation. We will need to be able to measure vapor pressures, and we'll need to be able to measure temperatures. We'll be able to find the delta H of vaporization of water by putting together a graph. Now, if you missed any of that, this is the partial pressure of whatever substance you're trying to study. For us, it's going to be water. R is the gas law constant. And it has different units than what we're used to. It's 8.314 joules per mole K. We also saw that gas law constant when we were doing fusion calculations. This is the temperature in Kelvin. This is the heat of vaporization. Again, we're studying water, so this is going to be of water. And then this is a constant. Now that equation looks kind of gnarly, and if you're not sure what that has to do with how we're going to do this lab, that's okay. I'm here to point out that this equation looks a lot like y equals mx plus b, which is the equation of a straight line. Now we have to manipulate the equation just a little bit to make it maybe more obvious. So that's what I'm going to do. The y would be the natural log of the partial pressure. The m is negative delta H of vaporization divided by R. 1 over t would be the x. And then the natural log of b would be that b constant. Now how this is useful for us is if we took some pressure data and some temperature data for water, and we graphed the natural log of pressure on the y-axis and 1 over the temperature on the x-axis, we would get a graph that looks like this. And if we drew a best fit line through that data, the slope, which is m, would equal the delta H of vaporization divided by R. So again, the slope is equal to the negative delta H of vaporization divided by R. So if we make that graph and we plot that line and we find the slope, we would multiply it by R, and that would give us the negative delta H of vaporization. If we're trying to find the positive delta H of vaporization like we are in this lab, we need to move the negative to the other side, and that would be positive. So the overall idea of part one is to make a graph, and then to use a best fit line to find the slope, and then to use that slope to calculate the delta H of vaporization. Now that wouldn't be very hard if we could just find the partial pressure of water. So this is just the pressure of water, and it's actually water vapor. But that's a little bit complicated. We've talked about how when you want to trap a gas, you have to usually trap a gas by bubbling it up through water or putting it in an inverted container in water so you can see where your gas starts and where the water around it begins. And so that's one of the complications for finding the partial pressure of water for this lab. So to make this graph, we're going to need the partial pressure of water, and we're going to need the temperature in Kelvin. If you've watched my video on the setup for this lab, or you've read the lab really carefully, you would know that the way that we're going to collect our data is that we are going to take a beaker, we're going to put some water in it, then we're going to put a graduated cylinder inverted upside down in there, and the graduated cylinder is going to have some air trapped in it, and it's going to have some water in it. So all this here is all water. And there's a little bit of gas, air gas, trapped in our graduated cylinder. And the gas that we trap in this graduated cylinder is actually some air plus some water vapor. We can't really get one without the other because we're kind of surrounded by air, and our air has water vapor in it. That's what we call humidity. But also because it's in equilibrium with this water, as we heat it up, some of the liquid water is going to become gaseous water inside that volume of gas. So that trapped gas is air and the water vapor, which means that even if we could find the pressure of the gas that's on the inside of here, the total pressure, which is the only thing that we can really measure, is equal to the pressure of the air plus the pressure of the water vapor. And we really only care about one of those. We really only care about this portion. But when we measure the pressure of the gas, we're going to get all of them together. So what we're going to do is we are going to measure the total pressure. That's actually the room pressure, which we call the barometric pressure. And we're going to measure that total pressure, and then what we're going to do is we're going to subtract out the partial pressure of air. So to make that look a little clearer, what we're going to do is we're going to measure barometric pressure, and then we are going to subtract out the partial pressure of air, and that will equal the pressure of water, which we'll have for that. Now to find the partial pressure of air, we can use PV equals nRT, and we'll put in the pressure of air here. We'll need to know the moles of just air. And when we rearrange that, the partial pressure of air will equal the moles of air times R times T divided by V. So now with that in mind, we actually need to know, instead of just a pressure, we also need to know the moles of air. We need to know the temperature, which we already have, and we need to know the volume. And let's go through those kind of one at a time here. To find the moles of air, that's a little bit tricky because we don't have an instrument that tells us the moles of air. And since we're always working with a mixture, we need to figure out how we can find a situation in which the gas is just air or just water. And luckily, if we took our data correctly, we have one data point. It's the lowest temperature point. At really low temperatures, somewhere close to 0 degrees Celsius, the vapor pressure of water is essentially 0. So what that's saying is that really cold temperatures, humidity is close to 0. And when that's true, the barometric pressure, or the room pressure, which is normally the vapor pressure of water plus the vapor pressure of air, this one goes to 0 at that low temperature. And so the barometric pressure is equal to the pressure of just the air. We can then use that pressure of air, measure the volume, divide it by R and T, and we can find the moles of air. So here, we can use the ideal gas law as long as we're taking the temperature that's close to 0 degrees C and the volume when the temperature is close to 0 degrees C. So those would be your lowest data points. This. So as long as you do it at that low temperature, you can calculate the moles of air. So I'm going to clean that up a little bit. Just kind of rewrite this so that we can keep track. So we're going to use the low temp and volume to find the pressure of air. To find the moles of air. So we have a lot of things going on the screen here, and I'm just going to kind of go through and write down the pieces of information that we need. Okay, so we need a bunch of temperatures in Kelvin, and we're going to measure those in Celsius, and then we'll convert them to Kelvin. We need to know the barometric pressure, we need a bunch of volume and temperature data. We already have the temperatures, we just need the volumes that correspond to them. And when we say volume, we're measuring the volume of this gas in here. And then we need one data point at a low temperature and its corresponding volume so that we can find the moles of air. Okay, so the data that we would take in this lab is we would measure a temperature in Celsius, and so we would have some temperature data here. We would also measure the volume of the gas in the graduated cylinder, and we'd be taking volumes here. We would measure the barometric pressure once. We would use the barometer on the wall in our weigh room to find that pressure. And we need to manipulate that data a little bit before it's ready to be used in the ideal gas law. We would also then have one low temperature and volume, so that would be our low temperature and our lowest volume down here. Now I said that we need to manipulate this data a little bit so that it's ready to be used in our calculations. We are going to convert all our Celsius temperatures to Kelvin, like we normally would. For the volume of the gases, we are measuring the volume of gas in a graduated cylinder that is upside down. And so this is like the 1, this is the 2, this is the 3. So it's upside down in a beaker itself, like this. And there's some gas trapped up here. And then the rest of this is water. Okay, so to find the volume, we would just be measuring this volume on the graduated cylinder. But what's tricky is that this is a meniscus here. And remember, we always read to the bottom of the meniscus, but the meniscus actually has some thickness, especially when our graduated cylinders are so small. And the fact that we're reading the graduated cylinder upside down means that the meniscus is actually adding to the volume instead of subtracting from the volume. So for each one of our volumes, we need to subtract 0.2 milliliters to account for that meniscus. All right, the barometric pressure we're going to measure it in millimeters of mercury. It needs to be converted into atmospheres. And then again, the low temperature and volume would be used to calculate moles of air. And you only need to do that once, just for the low temperature and volume. Now, if you follow along with the lab and do the procedure, you'll have data on your data table. And the results and data analysis section will lead you through these steps here. And when you're done with the results section, you will have produced a graph that is the natural log of the vapor pressure of water versus 1 over the temperature. There'll be some data points, and you'll have a best fit line. You'll have the equation of that line, but yours will actually have numbers. So it'll be y equals some numbers times x plus b. And those numbers there are the slope. And you are going to use that slope to find the delta H of vaporization. Now remember, when we're going from the slope of the line to the delta H of vaporization, we talked about how the slope is delta H of vaporization divided by R, and there's a negative there. Okay, so that's what the slope actually represents. If we're trying to solve for the delta H of vaporization, the first thing that we're going to do is we're going to multiply both sides by R so that those cancel out, and you would get the negative delta H of vaporization equals the slope times R. And then you just want to move the negative to the other side. So you're basically multiplying this side by -1, by -1, and so you would get the delta H of vaporization equals the negative slope times R. All right, so that's how you're going to use your slope to find the delta H of vaporization. Okay, so that's the theory and how we're going to use our data to find the results for part 1. Let's talk about part 2. Part 2 is trying to use some data to find the delta H of fusion for water. And again, the reminder there is that the delta H of fusion is the energy needed to melt solid water, which we call ice, to liquid water. Okay. And to think about what kind of data we're going to need, we're going to have to reach back to our thermochemistry equations and kind of review a couple topics there so that we know what kind of data we need to be able to find this number. The first thing that I want us to remember is that anytime we have things in thermal equilibrium with each other, that means that they're touching and able to exchange energy. Energy is always going to be moved from the thing with more energy to the thing with less energy. And the way that we set that up is we use Q to represent the energy, and we say that the energy lost by one thing is the energy gained by the other thing. And what we're going to do in this experiment is we're going to set up a coffee cup calorimeter. It's going to have some warm water in there. We'll know the mass, and we'll know the temperature of that warm water. Then we're going to put in some ice cubes that are at 0 degrees. And we're going to put that ice into the water, and the water, its energy is going to be used to melt the ice and then to heat up the water that is produced from the melting ice, and they're going to reach a final temperature together. Now, if we think about this in terms of energy, the water, the warm water, starts off at a pretty high energy, and the ice starts off at a low energy. Now, because we're going to put them in thermal equilibrium together, they are going to meet somewhere in the middle. The warm water is going to give energy to the ice because the warm water has more. And what's going to happen is the warm water is going to start giving energy to the ice. The ice is going to first melt, and that's the delta H of fusion. And then once all the ice is melted and made liquid water, the liquid water that is at 0 degrees, because that's the melting point of ice, so the liquid water that's at 0 degrees is going to start warming up, and it's going to meet with the warm water in terms of energy. And so the warm water is going to cool down, and the ice water, the water that is made from the melting ice, is going to warm up. And they're going to meet somewhere in the middle, which is what we call thermal equilibrium. If we look at our equation here, the warm water is going to be the thing losing energy. So that's going to be this one. And the ice is going to be the one gaining energy. So we could write this, that the negative Q of the warm water equals the positive Q of the ice. And if we expand that, just kind of putting in some more details, we said over here that what's happening to the ice is actually two steps. First, we need to melt the ice, and then we need to warm up the ice water. Now remember, back when we were talking about thermochemistry, we talked about any time we're trying to warm something up or cool something down, that's a temperature change. And the equation that we use to figure out how much energy it takes to warm something up or cool something down is C times M times delta T. And those variables are the specific heat, so that's C, M is the mass, and delta T is the change in temperature. We also talked about how when we're trying to calculate the amount of energy that it takes to melt something, that would be the delta H of fusion times an amount. So in here it's going to be our mass. So the delta H of fusion times the mass is the amount of energy it takes to melt. So I'm going to take that information and put it into our equation. So we'd have the amount of energy that it takes to melt the ice plus the amount of energy that it takes to warm the ice water. And if I expand that, Q to melt is the delta H of fusion times mass, and Q to warm the ice water is C times mass times delta T. So far, these all seem like things that we can measure. We can measure masses. We can look up the specific heat of water. This is the mass of the liquid produced from melting the ice. We can measure a change in temperature by putting a thermometer in our coffee cup calorimeter. So we have all the variables from this side to find the delta H of fusion, but we still have this part over here. It just says the negative Q of the warm water. So the Q of the warm water is the amount of energy that the warm water is losing by cooling down. And cooling down is a temperature change. And so anytime we have a temperature change, we can use the equation Q equals C times M times delta T. So I'm going to go ahead and put that in on this side. All right, so I need a little bit of room, so I'm going to start out here. This is the C of water, so that's a specific heat of water, times the mass of the warm water, times the temperature change of the warm water. And then I'm just going to rewrite this other side. Delta H of fusion times the mass plus the specific heat of the cold water. So that's I say cold water because that's the water produced by melting ice. The mass of the ice water and the temperature change of that ice water. So what I've done here is I've just kind of written the equation a little bit bigger just so that we can kind of review, summarize what's going on here. So we started with this equation saying that the amount of energy that the warm water loses is equal to the amount of energy that the ice and the water that's produced from melting the ice gains. I then expanded both sides so that we can see what kind of data we need to take to find these numbers. To find the amount of energy that the warm water loses, we would use the specific heat of water, the mass of that warm water, and the temperature change of the warm water. To figure out how much energy the ice and the water produced by melting the ice gains, we would have to first calculate how much energy it took to melt the ice. So that's the delta H of fusion times the mass of the ice. And then we would have to figure out how much energy it would take to warm up the water that is produced from melting that ice. So when the ice melts at 0 degrees, it's going to produce some liquid water at 0 degrees. And to figure out how much energy it takes to raise it up to the temperature that meets the warm water, we would use the specific heat of water, the mass of that water made from melting the ice. The mass of water made from melting ice is equal to the mass of ice. If that doesn't seem obvious, If you melt 10 grams of ice, you get 10 grams of water. So the water made from melting ice is equal to the mass of the ice. And then we also need to know the temperature change of that water that was made from melting the ice. And when we put that information together, we get the energy to warm the water made from ice, from melting the ice. Okay, so when we look at this equation overall, we need to know some specific heats, some masses, some changes in temperature, mass of ice, specific heat, mass, change in temperature. When we have all those things, we can put them together and do some algebra to find the delta H of fusion. That's the one we're looking for. Everything else we can either look up or measure. Now this equation is given to you in the results section. It's your job to take your data and put it together into each one of these parts that you need and to algebraically find the delta H of fusion. So overall, in this lab, for part 1, we're going to use volume and temperature data in the Clausius-Clapeyron equation to find the delta H of vaporization of water. And then in part 2, we're going to measure some masses and measure some temperature changes in a calorimeter, and we're going to use those to find the delta H of fusion of water.